So what I want to do today is continue our discussion on AI project strategy. So if you're building a deep learning system for some tasks, and today, for the first part of today, I'm going to use a speech recognition voice-activated device example. And then for the second half, I'm going to use a kind of AI deep researcher example. But what I want to do is walk you through a couple concrete examples of, projects you might work on, and let you understand what it feels like to be in the thick of building an AI system, making day-to-day decisions on what to do next. I find that, I think as you've heard me say before, understanding the algorithms is important. So in this class, you learn a lot, from the online videos about the deep learning algorithms, how to build pipelines. But even beyond understanding how the algorithms work, what really drives performance is a team's ability to have an efficient development process. How do you tune hyperparameters? How do you collect data? When you try something and it doesn't work the first time, which it often doesn't, what do you do next? Your skill at making those decisions is what often makes a massive, literally 10x difference in productivity. And as I was reflecting, was preparing for what to say to you today, I was reflecting on quite a few projects where that 10x difference in productivity is really not an exaggeration, right? Maybe more than 10x, but I've literally seen many teams in many, well-known companies with good brands spend a year working on a project that I will see a more skilled team execute in like a month, right? So these differences in skill are real. And one of the challenges for any people learning this is if you work for some company, maybe you work on a different project every year or two, right? But so it takes you 2 years or a year of your life to gain experience on one more project. And then after, 10 years, you've finally seen 10 projects and are pretty experienced. But what I want to do is, in today's class, walk you through a few concrete examples of projects that similar to the ones, kind of simplified versions of stuff that I've seen myself to try to accelerate your hands-on experience looking at these projects and thinking through if you are the one in the hot seat building a system and it works or doesn't work or there's a problem or whatever, making those decisions for what you would do. So try to get you through that today with a couple examples rather than you having to spend years and years of your life to finally see a small number of examples of how these projects can be driven, right? So the first two motivating examples I'm going to use today is building a voice-activated device. In my house, I have, like a Amazon Echo, right? I have a lot of them actually, and I think it's a delightful experience. But those devices like that, Amazon Echo or Google Home or the Apple Siri HomePod, they require quite a bit of setup, right? They require some setup. You're connect to the Wi-Fi, figure a way to connect to your phone, blah. And so, actually for a long time, even though I built smart speakers, for a long time in my house, I had one light bulb connected to my home Wi-Fi internet, because it's just so much of a hassle to set things up. I think now I have two light bulbs connected in my house. I guess I should connect more stuff. But so for this modeling example, I want to talk about if you are part of a startup building a new product that makes it much easier to get these voice control devices without the user needing to do this home Wi-Fi setup process. So, I'm not very good at drawing, but if you could go to some store and buy a desk lamp, and if the desk lamp already has a name, I'll just call this lamp Robert, and you could just take it, plug it into electricity, plunk it on your desk, and then say, Robert, turn on, and then it turns on. Say, Robert, turn off. That turns off without needing to be connected to the internet, so there's a cloud access and all that. Then that would give users a easier setup experience. There's a project that my friends and I actually discussed a few years ago that we thought would actually be a decent startup idea. We decided not to do it because there were too many other ideas that we're even more excited about. But we felt that actually, like a reasonable startup idea to build a little IC circuit, little integrated circuit to sell to, say, lamp manufacturers and other device manufacturers to make it really easy if say, some company sells lamps to build little things so they can very quickly make their devices voice enabled. And if you have a few pre-built names. Maybe give the users a choice. You can call your lamp Robert or Laner, or I don't know, or Johnny, or I don't know, Alice or whatever. Have a little switch. Then users could just buy a lamp, put it down, and then immediately have it be voice controlled without needing to worry about how do you get this onto my Wi-Fi network, and if my internet is down, then my whole house stays dark as well, bizarre things like that, right? And I actually did once I was building a lot of voice assistants. I actually set up my office to have a lot of voice control devices. So had different names with different lamps. Standing desk is his name as well. So I'd say, I forget what my desk name was, Jonathan, go higher or whatever. And then my standing desk would go up and down. It's actually pretty cool. So what I want you to, just for today's illustration, probably we should give the different devices different names, because you can't have every device in your house called Robert. Otherwise you say, Robert, turn on, the whole house illuminates. Then Robert, turn off, whole house is plunged into darkness. So we found out you do need different devices to have different names. But just for today, I'm going to use as illustration the task of training a neural network or building a system that detects when someone says, Robert, turn on. And you need kind of Robert, turn on, Robert, turn off. If you have a choice of names, it would be Lena, turn on, Lena, turn off, a variety of handful of options of names. But just for simplicity, I'm going to worry only about detecting the phrase, Robert, turn on. Right? And whatever we do for this, you can rinse and repeat to get the turn off command and a handful of other names to make it user selectable. What name do you want to give this thing? Okay. So, this is something they'll need to run on device, small IC circuits. And I'm going to ask you a question, right? When you've graduated from CS230, or maybe when you graduated from Stanford, if you are the CTO of a startup responsible for building this, what would you do? Right, so call out. So imagine you just graduated from CS230 or just graduated from Stanford, and you're the CTO of a startup, and you want to build this lamp that can turn on when anyone says, Robert, turn on. How would you approach this problem? And I know this is an incredibly open-ended question, and it turns out life is incredibly open-ended, right? You graduate from CS230, you have to decide what to do. So if this is what you're doing, feel free to raise your hand and call out. If you want to build this product, what's the first thing you do? How would you think about it? Go for it.
The speech to the explorer, and then the speech to the explorer to have the actual work, and then kind of compare the work with what we know. And you like one straight up and zero always.
Yeah, cool. Yeah, right. So get some like an open source speech to text model or something, and then see if you can run. Yeah, that'd be a good start. Anything else? Yeah, go ahead.
It's related to three models. Increasing complexity. The first one will detect audio, just going audio. The second one will detect the word Robin, and the third one will try to parse the phrase that comes after that.
Oh, wait, sorry. 3 models. One that detects Robert, and then one that.
Well, the first one detects the word sound.
I see.
The second one detects the word Robin. The third one tries to understand what the sentence is after the word Robin.
I see, cool, right, okay, right. So 3 models to detect Robert, understand the rest sentence, or detect the sound. Cool, go for it. Oh, sorry, say it again?
I would do the review because, like, if we have a model that only detects Robert, then let's say you want to expand your company and have different circuits with it. Then you have to repeat like the same process for Jane, Alice, whatever. So instead, I think what you could do is take a model that takes given like reference audio file and another audio file and see like train it to identify when the 2 files say the same.
Okay, oh, interesting. Oh, it's like a Siamese network. We actually teach a Siamese network later in this class, where something that inputs 2 audio files and decides they're saying the same word, so you can more easily generalize to new words than Robert. Cool. No, that's actually pretty interesting. Yeah, go for it.
I don't know how to read this device was enabled, but I think it may be simpler way to just have some plugin on and like have a program on my mobile. So like kind of like it's like Siri. So I can go like image activate it on mobile and my mobile will just send and or like turn on to device.
Oh, sorry, you mean just connect up your device to Siri?
Yes, so kind of like neural network will be wait on my iPhone, and the iPhone will send the signal to the device to turn on.
I see. Okay, cool. Yeah. Right. Yeah. That sounds interesting. It sounds like a different product than this if we need to connect it to your cell phone and all that though. Yeah. Cool. Right. So let me just, lots of interesting ideas. Let me just make some observations. So I find that when building software products, there are actually lots of good ideas or lots of reasonable things you could try. But, you know, as you heard me mention a few weeks ago, I think one of the strongest predictors for the odds of you building something compelling is speed. So I find that of all of these ideas, I think some are better than others, but it doesn't. But whether the idea is, you know, a bit better, a little bit worse, it is important, but it's actually secondary to how quickly you can just get something built. So if you're actually the CTO of a startup like this, I would encourage you to look and say, all right, what can we build, you know, today, or what can we build maybe in a week, and try out any of these architecture choices and build it and see what happens. Because even if what you build is a little bit less, you know, good, you can find out in 2 days, you know, then you can course correct very quickly. I've actually built a lot of smart speakers. So I have maybe first-hand experience of this, and I just share some things that I happen to know that there's no reason you would know. But it turns out that, let's see, at least today, general purpose speech recognition is still a little bit heavyweight. It takes quite a lot of, you know, processing power. Is a bit expensive to run on an edge device if you want to make this like just a few dollars. But it turns out that if you look at the smart speakers, there's usually if you want to train a neural network just to detect one phrase, be it a phrase like, you know, OK Google or Hey Siri or Alexa or whatever, and the smart speaker trigger words, that can be done with a fairly small neural network. Although to your point, if we want to do different neural networks, different words, we'll need to swap out different neural networks and rinse and repeat that. But if you have only a small handful of names, phrases one to detect, I think that'll be okay. And then one other piece of advice I would give, if you're embarking on this, is the first thing I would do actually, if I was working on this for the first time, is actually a literature search. And it turns out that, you know, I think we're fortunate that the AI world has a ton of open source software and a ton of open research papers. Somewhat surprisingly, despite smart speakers haven't been around for a long time, there still to this day isn't like a single architecture that everyone's agreed on the best way to do this. If you look at the literature, there's still actually a diversity of opinions on how to do this type of wake word or trigger word. We use those terms. So when you say something like, you know, OK Google or Hey Siri or Alexa, that's sometimes called a wake word because it wakes up the device, or a trigger word, it triggers the device's take activity. So somewhat surprisingly, even though we have smart speakers for a long time now, for a lot more than a decade, there still isn't a single agreed on unified architecture that the community has agreed on what's the best algorithm to do this. But I feel like if you are embarking on this for the first time, the number one boost in your speed of learning, it could be implementing something, but I would say doing a literature search and trying open source software would be the even faster accelerator. And I want to give you a few tips for that, right? Real quick. So, you know, today, if this is, there are a lot of research articles and blog posts and GitHub repos on many topics, certainly wake word detection. And what I find is that if this is research paper 1, research paper 2, research paper 3, research paper 4, I find that, you know, sometimes people will spend a lot of time reading research paper 1 until you're done. Right, it's 0% complete, this is 100% complete. And then spend a lot of time reading research paper 2, spend a lot of time reading research paper 3, and I just recommend you not do that. Instead, when I'm doing a literature search, what it often feels like is, do a few web searches for a handful of resources, skim all of them, 0% complete, 100% complete, right? Based on initial reading, you may decide to go back to paper 3 and spend more time to really read and understand that, but that'll help you find additional references that you can skim, and maybe you find a paper 7 that's really seminal, spend a lot of effort, but this is what doing a very broad survey of the literature will feel like, where you really put in the time to finish only a very small number of resources, but spend a lot more time skipping around and getting a cursory level understanding of a broader set of papers, which can also point you to the more useful resources to focus attention on. And just one other thing I've seen among Stanford students, there's one other thing that I find people tend to underuse, which is trying to talk to experts. So if you are actually a C-level startup trying to build this for the first time, I feel like, we all want to do our own work and not bother other people, which is good. But I just encourage you to consider if, after you've done your own work, if reach out to an expert can really accelerate your learning. So something I've often done is, I will do my own work, right? I don't want to call random experts to try to bother them before I've at least done my work. But if you've sometimes I'm reading a paper, I'm really struggling to understand it. And I find that instead of me struggling for another 4 hours, if I send the authors a respectful email and say, hey, I read your paper, try to understand this, I'm still confused. Can you help me out? Can you explain this to me? A lot of the time, including when, I was less well known, right? But I think a lot of people, if they see that you're doing your work and not just reaching out to them before you've even done anything, a lot of, not everyone, but a lot of research authors would actually be quite, understanding and try to help you out. And so I find that for a lot of projects I did, finding that one expert, sometimes a Stanford professor, actually, we have a lot of speech faculty in the Stanford faculty as well. But when I had problems with my speech recognition system, sometimes I call Dan Jurowski, whatever, and then a half-hour conversation or even a 10-minute conversation really accelerates what I've been able to do. So I just encourage you to, it takes you 10 minutes to send an email, and maybe there's a 50% chance to respond. I don't know, right? Not a 100% chance, but sometimes that tends to be really high ROI, right? And then what I think you find is that if you do a literature search, you will likely discover that most of the robust enterprise-grade smart speaker systems all have a specialized system trained to detect the wake word or the trigger word, right? And again, there's a variety of architectures. You probably come up with some good neural network architectures for this. It turns out that there is no data set on the internet with lots of people saying Robert turn on, right? That's just not a thing, right? So if you decide that the names are Robert and Lena and, I don't know, Jeremy and Alicia or whatever, sorry if there are people with those real names. It was actually kind of weird when we chose people's names, but we just did that for some reason. But it turns out that there is no large data set on the internet of lots of people saying Robert turn on. So if you want to train a neural network to detect if someone has said this phrase, you need to collect that data yourself, right? So let me then ask you another question. Say you've done a literature search, found some open source code you can try, but that has led you, say, to conclude that you need data sets of people saying Robert turn on. You need a data set to train to distinguish between someone saying Robert turn on versus not someone saying Robert turn on. How would you approach getting a data set like that? So yeah, go for it.
Text to speech.
Text to speech. Mm-hmm. Yeah, cool. Yeah, yep. You use text to speech as one method. I'll come back to that later. So you need ideas. Go. Oh, sorry.
Just take one of those sentences, go to canvas and ask people to speak.
Yeah. Yeah. Yep. Cool. Yep. I like that. Yep. So walk around and ask people, tell them what you're doing, get the permission to record and use their voice. And then if they're okay giving permission, just record their voices. Yeah. I like that. Anything else? Cool. Yeah.
Basically, the phrase that the other officer is set.
Oh, sorry, can you say that again?
So like in the training sample, like we should have samples where there are return officers and then there's like also samples where there's not.
Oh, yep, cool.
Indication.
Yeah, yep, cool, yep, right. So samples of people saying not Robert Turner-on, not people, yeah, yep, agree, yeah, cool. Good.
Part of the innovation that we do is like going around and asking like say Robert Turner. I would also have to say sentences with the word Robert in it and classify those as not as it's like I don't want to just activate.
I see, cool. Yeah, actually, you're right. So the data is what people are saying Robert, but you don't want that to be mistaken. That's a good point. I'll come back to that later. But yes. Did you say something? Oh, same thing. Oh, interesting. Cool. Awesome. Great. All right. So one of the so I really like the idea of just going around and asking people for permission to record their voices. And by the way, in today's world, privacy is important, consent is important. So don't do anything sneaky or weird, right? Just tell people clearly what you're doing. Ask them for permission. Make sure any permission is freely given. And if they don't give permission, it's fine. Move on. They really respect people's privacy. That is really important. Having said that, I find that a lot of people in the world are very nice. Not everyone, but the vast majority of people in the world seem very nice. And if you ask them nicely, I know this because I've done this myself. They will give permission for you to provide their data, right? So then just one of the framing I encourage you to think about as always is the speed. So how long will it take you to wander around campus or wander around San Francisco and collect a sample of voices? And I think you actually get a lot done. Get many dozens of samples, maybe hundreds of samples easily in a day. So I think those are good tactics. And then let me share with you some things. And then it turns out synthetic data using text-to-speech is an interesting tactic. I would usually not use that as the first thing I do, mainly because it turns out it's hard to know how accurate synthetic data is compared to true, natural data. And maybe just share you one thing I've run into. I've actually, done a lot of synthetic data for speech recognition, right? One thing you have to watch out for is if you go to a lot of the synthetic, sources of data, how many different voices does it provide? And is it going to be a pain to get enough, diversity in different people's voices? So it turns out, I don't know, like, for example, I often, talk to OpenAI voice on my phone, right, instead of typing, but the number of voices there is limited. And if you go to a TTS provider, I guess there are now some services with a larger number of voices, but these are things you end up worrying about. And it's all solvable. Synthetic data does work for speech recognition, right? But it turns out that there are often enough details associated with filling with the synthetic data generation process that ends up taking longer. So for a lot of machine learning applications, using synthetic data is a good idea. And eventually you might get around to it, but using synthetic data is usually not the first type of data I would collect, because usually there are just too many hyperparameters and too many knobs you have to worry about. And then at the back of your head, you're wondering, what if there's something, weird about the synthetic data that I had not thought of before? And once you collect natural data, collect real data, it's just one less thing to worry about. Maybe just tell one more story, not in speech, but self-driving cars, right? So if you're building self-driving cars, you want to detect other cars. Where do you get pictures of cars? It turns out that a lot of people will have the idea of, there are lots of video games with cars driving around. Why don't we use video games to get pictures of cars out of the video game? But it turns out a problem with a lot of video games is there could be like 20 different cars in the entire video game. Depends on the video game. But it turns out that to have a realistic video game, you don't need 1,000 different cars, and there are tons of different car designs on the road, but you need a very narrow set of cars. And so to a human, seeing the same 20 cars over and over, it looks like a road, looks fine, the video game plays fine. But for a lot of video games, the data just isn't rich enough to capture anywhere near the richness of the real world. Whereas in contrast, if you've got raw pictures, there's just one less thing you have to worry about, right? So I find that for synthetic data, it works, it's very valuable tool, use it a lot, but I usually get to it only later in the process. Does that make sense? Cool, so thank you. So, and then in the interest of building these things quickly, let me share with you the types of things that my teams have done to collect data for this, right? And I feel like when you read research papers, or you take courses, often you get a very clean view of data. I'm going to tell you about one of the weird random hacks that one of my teams has used to build like a very serious, working really well commercial system. Right, and at least as part of the journey to do so, which is let's see. So, right. So collected 100 training audio clips and 25 development set to tune to, and 0 tests. Right. One thing I'll often do if my main goal is to just build a system that works, as opposed to publish a research paper, is to not have a test set. We just have a dev set that we will tune the parameters to. And if I want to publish a research paper, I probably need a clean, unbiased test set. But if my goal is to just build something, and have it work and ship it, sometimes I just say, I'm not going to bother to collect any test data, just a training set and a dev set, and I just unapologetically tune my system to the dev set, right? And one thing you could do is, let's see. So audio clips. So audio is, let's see. So you may have seen the audio waveforms, right? Which one? There's time, x-axis is time, and audio waveforms kind of are these wiggly time series. Right, and sound is very rapid vibrations in the air that your ear perceives as sound. And what a microphone does is it records these very rapid changes in air pressure. Right, so that's why you see audio waveforms that look like this. And so one thing that one of my teams once did was collected 100 samples of audio waveforms, where somewhere in the middle of it is someone saying "Robert, turn on." So, hey, how are you going? Oh, yep. And let's say Robert turn on, and we can now talk about some other things, right? And so the phrase Robert turn on takes about 1 second to say. And one way to construct a training set would be to take a 3-second clip. Oh, so this is where Robert turn on was said. This is where they just finished saying Robert turn on. And so if you collect 100 audio clips like this, one way to turn this into a bigger training set is to take these long audio clips, and then this becomes a training example with a label 1, because that's an utterance where the end of the utterance corresponds to when someone just finished saying Robert turn on. And in contrast, this would be an example, would be a negative example. And this too is a negative example, and this too is a negative example. Does it make sense? So given a, say, 10-second clip, given 10 seconds of audio, we will have cut out a phrase where you get a positive label if that 3-second audio corresponds to someone just finishing saying Robert turn on, which is when you should turn on the lamp. And anything else is labeled 0, right? And so this is a way to take, say, 100 training examples and turn that into 3,000 binary examples. So 100 audio clips, sorry. I should say 100 audio clips. Right? And if we take 30 windows out of this, then you can turn this into, say, 3,000 training examples, each with a binary 0 or 1 label. That labels is this moment in time when someone just finished saying the phrase, Robert, turn on. Right? So it turns out that if you do this, and we did do this, then we wound up let's see. We wound up with a system. So we ran this and tested this on the dev set. And we wound up with a system that when trained to predict binary classification was 97% accurate. Right? But it turns out it did this by outputting 0 all the time. That had 0 detections, right? And so with this training set, we basically trained a very large neural network where I would have gotten exactly the same result with that one line of Python code, right? So this is the kind of stuff that happens in real life, right? And by the way, I'm sharing these stories not just to entertain you, though hopefully you're entertained, but because I think it is by living these experiences that you go, oh, I could see this problem. This is what I do. I could see this problem. So my question to you is, if you collected this data, trained the system, 97% accuracy, isn't that fantastic? But you realize that you just implemented via a huge neural network a print 0 statement, or the equivalent of print 0 that is never finding the phrase raw return on. Like, what do you do next? What's going on? What do you do next? Oh, please. Yeah, cool, awesome, right. So increase the number of raw return ons in the training example. This is a very unbalanced training example, and it's did great by just saying, I never hear this phrase, right? How would you go about, and you or anyone else, how would you go about increasing the number of positive examples? Go for it. Oh, but how do you do that? Oh, audio editors. I see. Wow. I see. Cool. Yeah, interesting. Okay, yes, that would work. That gets the synthetic data again, right? Which actually works, and it also has all the complexities of synthetic data. But it turns out it does work, so I know it works because I've done that too. But yeah, wait, I see. Go ahead.
You can always take your example already, duplicate this.
Yeah, yep, that works too. So one thing you could do is take your positive examples, the examples of raw return on, and just duplicate those examples, or maybe just give those examples more weight to the training objective. Right? Yeah. Any other ideas? Did you want to say something?
I think similar situations. Take an example over increase the noise of that similar.
Oh, increase the noise of the example. Yeah, cool. Yeah, yeah. So a few variations of synthetic data generator. Yeah, yep. So I think the easy things to try, one would be to take the examples and duplicate it, right? So, mathematically, this is equivalent to taking your positive examples and just making multiple copies of that in your training set. It turns out that will work. They'll largely solve it. And by the way, unbalanced data sets is a common issue in training neural networks. I'll tell you the rule of thumb I use, and is many neural networks are pretty good at handling up to like a 1-to-10 ratio of unbalanced data sets. So people often worry, what if an unbalanced data set? In this example, we have like a 1-to-30 ratio, and your mileage may vary. Sometimes it works, sometimes it won't. In this case, it didn't work. But I find that if you have like a 1-to-2 ratio, just usually not that worried about it. Neural network is fine training like that. Maybe up to 1-to-10 is when I start to worry about it being a little bit too unbalanced for standard training procedures, and when I might do something to make it a little bit more balanced. But duplicating the examples would be one tactic. Go ahead.
What if you also penalize false negatives?
Yes. So penalize false negatives. Yes, that would work too. So I think there are a few ways to to change the cost function. You can give the positive examples more weight, or or penalizing false negatives would be another way to change the cost function. That will work. Yep, that will work too. Okay. Go ahead.
We also work to increase the amount of the negative samples. So instead of creating versions more specific than the existing
Yeah, yes. So you can also decrease the number of negative examples. That would work too. The one downside of that is, it's okay. I think it's fine to do what you said. The one slight downside is if you are reducing the diversity of the negative examples, then the neural network has just a little bit less information to learn from. I think this is what I just said is a small difference, though. I think that would also work as a quick thing to try. Yeah. And I just tell you I'll tell you what my team actually did. And I'm telling you this not because it's a brilliant technique I'm proud of, but because I just want to tell you the examples of the types of hacks that actual commercial machine learning teams do that actually works, right? So I'll tell you what we did. It was very close to duplicating the positive examples, but we had just a slightly different variation, which was we said that instead of the positive example being the one window where Robert turned on just finished. So here we're having a sequence of labels, right? Where 0 corresponds to is that moment in time when someone just finished Robert turn on. And in the architecture I described, we are detecting a very, very narrow window in time where someone just finished Robert turn on and they got to turn on. But the hack that we used was actually just extend this out a little bit. So instead of saying, did someone just finish saying Robert turn on in the last 100 milliseconds, we extended that out to half a second or a second. And so if someone finished saying Robert turn on anytime in the last half second, let's turn on the light, right? And so this actually generates a few more training examples. The reason we did that, and again, it's a small difference, is this actually creates a little bit more diversity in the positive examples than just duplicating it. Because now this red rectangle is a positive example, and so is this one, and so is this one, and so is this one. So it just creates a little bit more diversity in the positive examples. I expect this will make a very small difference in the training, in the learning algorithm's performance, but it's just, maybe just slightly better to have slightly, so it covers the space of positive examples just a little bit, just very, very little bit better. Make sense? So, again, just to keep going with the story, let's say you do this, and now, you still do well on the training set. 95% accuracy on the training set, but 50% accuracy, so not good enough on your dev set, right? So you fix one problem, and another one comes up, and so what do you do next? Go for it. Yeah, cool, awesome. Yep, overfitting and use regularization. Go ahead. Is it that training and dev set distributions are not the same? In this example, because we collected the training and the dev sets, if we randomly shuffle between training and dev, then they would be the same distribution. Actually, yeah. But sometimes there's one other thing I do see, which is it turns out early in the history of machine learning, there was always this assumption or obsession with making the training set and the dev set and the test set have the same distribution. I think it's because if the training set and the test set have the same distribution, it's easy to prove theorems, easy to give guarantees, whatever. So in kind of academic machine learning, there was always this, theoretical assumption, which makes the theory work way better. The training set and your test set come from the same distribution, right? It's just like, from a publishing paper's point of view, that makes life much better. From a practical point of view, what I see is a lot of the time, your training set distribution is just different than your test set distribution. That's just life because, it's hard to demand data of a certain sort. And so, for example, one common thing is if you do use synthetic data generation, you can come up with really clever ways to generate synthetic training data, like using TTS or editing audio or whatever. These techniques let you generate a massive training set. But the price of that is, your synthetic data, that's not how users talk, right? Users don't speak synthetic data, they speak real data. And so to make sure that your test metric truly reflects how users will perceive your product, I would put true data in your test set. And so you end up with a lot of systems where your training set distribution is synthetic data or other things you fit it with. And then your test set is whatever the world actually cares more about, and the two distributions is very different. And then I think the question that you just asked is the training set distribution too different from your synthetic data that is a problem? Those would be good questions to ask. Right? All right. So if you see this is overfitting because we're doing great on training set, not so well on dev. So one thing to try would be, the first thing to try is regularization. So that would be a good thing to try. And then beyond using regularization, I find that for a lot of speech problems, if you're overfitting, getting more data is nice. And so just to share with you, I know suggestion of synthetic data earlier. I'll share with you one thing for synthetic data that does work, which we eventually wound up using, which is it turns out that this is audio stream, right? It turns out that there are a lot of if you can get audio clips of background noise. So for example, in this room, if I'm quiet, we can hear a little bit of air conditioning noise, right? So a lot of rooms have a little background noise. Or if you're near a highway, there's cars in the background. So there are actually most people where they may use the lamp, there's a little bit of background noise. So if you're able to get audio of background noise, and then additionally record some very clean audio clips of Robert Turn On, it turns out that if you take two audio waveforms and sum them together, you end up with an audio waveform that sounds like someone's saying this in the presence of the background noise, right? So I think it's called the superposition property of sound, but basically sound adds, which is why if you take two audio clips and you just add the audio waveforms together, then you end up with an audio recording that sounds like both sounds going on at the same time. So what we can do is take, background noise. There's actually a lot of audio clips of background noise on YouTube as well, and so on. That check the licensing terms before you use stuff like that, right? But there are actually quite a lot of openly licensed audio clips of, just someone like a coffee shop noise or someone sitting in a house studying or whatever. And so if you can take some background noise audio clips and then take a clean voice, someone saying, Robert, turn on, right? And if you add these two together, then you end up with background noise, Robert, turn on, and more background noise. And this becomes a positive example using the process that we talked about just now. And if you have a handful of clips of Robert turn on and a lot of clips of background noise, so you can synthesize the phrase Robert turn on against a lot of different types of background noise and create, a pretty large training set. It turns out one problem with what I just described is if you do exactly what I just said, you won't actually find a Robert turn on detector. You end up with a voice activity detection detector because you have a lot of background noise, and anytime anyone says anything, the only thing people say is Robert turn on. It's much easier to just decide, is there a loud sound of someone talking to actually recognize things? So the other thing we should do is instead of adding Robert turn on, pick a dictionary or find other types of audio. I think that's where you had the comment just now of make sure don't confuse other things and add, get someone to say the word, cardinal or whatever, or other words. So you have a bunch of examples of people saying words other than Robert turn on, and then also a bunch of examples of people saying Robert turn on. And by having a handful of clean recordings of Robert turn on and a handful of clean recordings of people saying other stuff and synthesizing a data set like this, you can get a data set with many thousands of examples of Robert turn on pretty efficiently. And if you train a neural network on this, you get like a decent wake word or trigger word detector. That makes sense? So, yeah, right. So, with a process like this, so this is what working on a machine learning project feels like, right? You try something, doesn't work. Like you find out that, you have a skewed data set, be creative in how you collect data. You may find that you have a skewed data set, it just doesn't work. You may find this overfitting. And I find that it is the ability to drive iterations on a system that determines how quickly you can get something to work. Right? Yeah.
Let's say we look at the background, for example, you want to have users that listen to music in their home. How would you account? How would you sample and train them all to differentiate text and lyrics?
So for the Robert Turn-on example.
Yeah.
So if I found that there are a lot of users that are listening to music, then I would probably synthesize data with music in the background and then have someone say Robert Turn-on. So if you think a lot of users listen to music and there's our desk lamp, we want to make sure we catch them saying Robert Turn-on, then I would probably synthesize more training data to include, loud-ish music in the background.
But the genre of music that you can't really predict what the listen to be vastly different to them all.
Sorry, what are the genre of music?
Like if it's like classical music or deep metal, which you don't know, like what they usually listen to, and then you train two different genres of music to the long, it's extremely different.
Oh, yeah. So it turns out that if you have I feel like as a rule of thumb, if you can have a more diverse set of training data, it's usually better, right? So, so maybe I'm not sure what music my user base likes to listen to the most. Is it classical? Is it rock? Is it EDM? Is it whatever? If you could collect a very rich training set that includes all of the above and even more, then usually they'll do better than going too narrow and risking picking wrong. Yeah. And the one asterisk to what I said is so long as you can train a neural network that's big enough, usually more diverse data, more diverse data is better. If your neural network is too small, then it may lack the capacity or the intelligence to memorize all this stuff, which could be a problem. You need a very small network that runs at the edge. But usually, if you have the capacity to get more rich, more diverse training data, that ends up delivering better results. Make sense? Cool. All right. Now, I want to share with you. So it turns out when you're building a machine learning system, very common experience is you try something and it doesn't work. And then you have to figure out all the wonderful ways it could be not working and then go and fix whatever is not working, right? And even in this, example we went through, is the training data too skewed? Is it overfitting? So you need either regularization or more data, or is it like something else? Or the synthetic data distribution not match your real data distribution? It turns out that when you're training a neural network, when you're building an AI system, it's really difficult to know in advance what's going to go wrong next. I find that in software development, if I'm writing traditional software, you kind of control all the code. And so it's more okay to write a spec and then you just build it and then it, kind of works. You still need to debug it, but the bugs are, it's like my own bugs, right? In contrast, when you're building a machine learning system, it's much more like, I don't know what's going to happen next, right? Maybe because I don't know what the data will give me, hard to predict how the algorithm will perform. And so the workflow of machine learning feels much more like debugging than development. And by debugging, I mean, it's this iterative process where you build a system and you're just repeatedly trying to find how it doesn't work and fix it. And if you're trying to do a task that humans can do, then the bugs or the gaps in performance is often whatever a human can clearly do, but the AI system is unable to do. So for many machine learning teams that, I've led or worked in, if you can get the team to healthy rhythm of this debugging cycle, you can make really rapid progress. So for example, it turns out, let me give one example. I've been on teams where we would do the following, right? Let me say morning, afternoon, evening, night. So we run our trading jobs at night, right? And for example, it turns out for some of these models we're training for speech recognition, let's say it takes 4 hours, right? So the training job takes about 4 hours to train the network. So training night, in the morning, we look at the results. Look at the results, do error analysis, try to figure out what's wrong. In the afternoon, we write code, right, to figure out how we're going to fix whatever thing we discovered the day before. And in the evening, right before we go home, we launch the training job. And then it runs overnight, and the next morning, we do it again, and again, and again. And it turns out that if you can fix one problem a day, that's actually pretty good. And within, and then you saw me walk through three or four problems. When I built this for real, there are slightly more problems than that, right? But I find that if you can get a team into a cadence where you train stuff, look at the results, figure out is this bias, variance, data mismatch. Oh, actually, this should be code or get data. Fix it, and in the evening, before you go home, launch the job. Maybe if you have time in the evening, just baby the trading job a little bit, make sure it's still running, but then come back in the next morning to see how it did. Then you just do this over and over, and it can make really rapid progress. And I find there's often this discipline, right, that lets you make progress. In contrast, the teams that kind of wake up and they go, what do we do next? Oh, let's call a meeting this afternoon. Wait, where's the data? Okay, I guess we'll meet tomorrow to look at the data. And then like, our infra is down. And teams like that move much slower than the really disciplined teams that just keep on rolling forward. And one more observation, it turns out the iteration cycle sometimes it is driven by this. So I've worked on machine learning jobs where it took us about 4 hours to train a model, and 4 hours is long enough. Don't want to wait for it, but running overnight is just fine. I've also worked on teams where a typical training job took about 3 weeks on average, right? And so if it takes 3 weeks to train a neural network for a particular type of model we're working on, then the pacing is very different. So how long it takes to train a neural network really drives the pacing of this, where sometimes we would, launch a training job and then hope for the best. We monitor it during those 3 weeks. It's not that we do nothing for those 3 weeks, but you just go launch a training job and then frankly, hope that it works 3 weeks later. But we take 3 weeks, and after that, tons of analysis and debugging and whatever work that would take us 1 to 2 weeks to set us up for the next training job. They're going to take us another 3 weeks to get a result. And then we're also parallelizing. While we're launching this job, we're analyzing the result from a previous job, and we launch a few jobs asynchronously. But I find that how long it takes, this is a huge driver for how you do this. The other end of the spectrum is if it takes 10 minutes to train a neural network, then that's wonderful. You just train it, get a result, train it, get a coffee, come back, then do their analysis. And then the bottleneck is how quickly can you analyze the data and get more data. So this really drives the design of this process. And one other thing that happens is for a lot of projects, you start off with a small thing that takes 10 minutes to train, but then as you get more and more data, then you're bigger than, but now it takes 4 hours to train. It goes even bigger. Then it takes 2 weeks to train. It's now this thing takes a month and a half to train. So I've experienced that as well, where unfortunately, as the performance climbed, we decided we had to train bigger and bigger models with more and more data. And then it went from this really fantastic 10-minute iterations to these month-long iterations. But they just had to be done because we were training bigger and bigger networks. Right? Yeah.
What type of things that you could do to change while the model is training? As you're getting to the model, and you see a problem, do you have to stop the model or
we probably didn't stop the model that much. So sometimes you can look at checkpoints, and if you see that for some reason, actually, if you're training a 3-week job, you kind of expect the performance to be at a certain level after a couple of days or after a week. And if it's way off, then before burning another 2 weeks, you may ask, is my learning rate clearly wrong? Or maybe this new data set we tried is clearly wrong. So you can actually start to run some analyses on the checkpoints, and sometimes we would yank the job and just kill it. I would say that happened very rarely. Yeah. Yeah, yes. So one thing you learn about in the online videos is transfer learning. We train a large data set and then maybe fine tune on just a much smaller data set. And then if you process a fine tuning a much smaller data set takes, half an hour, right? Then that's great. Then you can also drive much faster iterations, and that based on that half hour is a limiting factor for the training time. Cool. All right. One of the reasons I obsess about speed is because it turns out that if the x-axis, imagine you're building a startup to launch this product, right? I find that if a team takes, twice as long to do it, they're just much less competitive in the marketplace, right? So here's what I mean. So if this is era, and this is months, right? There's some machine learning systems that we work on for months to keep on trying to improve it. And if this is you, and if a competitor, say, takes twice as long to reach the same level point, so instead of taking this long to get here, they take this long to get here. Instead of taking this long to get here, they take twice as long to get here. So the competitor kind of does that, right? It's just take twice as long. They take 2 days instead of 1 day to do something, but they always take 2 days to do what you would take 1 day to do. Then the performance over time looks like this. And what the customer cares about at a certain moment in time is you are so much better than them, right? So these 2x differences in speed really translates into a massive difference in the performance of your system versus someone else's system in the marketplace. And I find that the fast-moving teams are just so much more effective. And you might think, I took 2 days, they took 1 day. What's the big deal? Like, the big deal is not that you're a day slower. The big deal is you're 2 times slower. And it's it's just in the marketplace, it's just not competitive if you take twice as long. For some applications. Okay? All right. There's one other example I want to cover. Let me try to do that quickly. So what I've talked about so far is speech recognition, wake word detection, which is more of an end-to-end deep learning system where you input audio, goes to a neural network, and then this outputs, is this RTO, Robert Turner, right? So the entire system you're trying to build is just a single neural network. For a lot of applications you build, you end up building pipelines, or sometimes call them cascades. So I'm going to use the term pipelines. We saw one example of this last time where to detect people coming up to unlock a door with face recognition, we had video that fed to visual activity detection to see if anyone is even in front of it. And then that fed to neural network to recognize, is this an authorized person? And then 0, 1 to say, is this a person that we should unlock the door for? Right? What I want to do is use a different example of a pipeline of an AI deep researcher. So it turns out, right, all of the, I think all of the leading LM, almost all of the leading LM providers have deep researchers where you can ask a query or go and search the internet, look at a lot of web pages, and come back and synthesize a very thoughtful report, right? And so, but I actually use the OpenAI deep researcher quite a lot. I think that I know some of the team that built it, and it's really well built. Although I think some others also did a good job. But so, you input a query like, this is an example I'm taking from the Agentic AI course online. But input a query like, show me the latest research on black holes, right? Some query like that. And then, one thing you might do is take a query like whatever, right? Black hole research. And then use an LLM, use a large language model to generate search terms to feed to a web search engine. So it may generate a few terms like, black hole research, latest in, astronomy and black holes or whatever. So generate a handful of search terms. This then call out to a web search engine, be it Serper, Google, DuckDuckGo, Bing, I use Tivoli quite a lot, but there are multiple, actually more and more web search engines designed for AI rather than for humans, which I think is pretty neat. So this can call the web search engine, and then fetch the top URLs. Fetch the top pages other than the top URLs. So if a web search engine returns 10 pages, you may not want to fetch all 10 of them. You can read the snippets, decide which ones are most relevant. Again, maybe with an LM, with a large language model, to decide what are the pages you want to download. So just like a human, I'll do a web search. I won't click every single link. I'll take a glance and then decide which ones I want to click. So identify and fetch the top URLs and then feed all that into writing, and this gives the final output. Right. So this is by the way, this is a more traditional deep researcher deep researcher architecture. The more modern deep researcher architectures let the system decide when to do more web search, when to fetch more web pages, and are more autonomous, more agentic. But this is what the early deep researcher architectures look like. There's more of a linear pipeline. There are more modern architectures where system will fetch some pages and autonomously decide, do I need to go back and do more research and on what topics and iterate a few times? But this would be like a pretty decent basic deep researcher, right? And it turns out that if you actually build this, in the speech recognition system, Robert Turing on LAMP example, we talk a lot about how to improve one component, which is a neural network. If you have a pipeline like this, the other thing you need to do, which is critically important, is to decide of all the different components in the pipeline, which one do you want to focus your attention on, right? So I find that one thing that makes a huge difference in a team's performance is, again, being able to drive a disciplined evaluation and error analysis process to decide what to work on. I find that a lot of machine learning is not, wildly doing things to see what works. It's actually a very thoughtful, very disciplined process where the system, maybe it's not doing as well as we wish, so we should look at it to decide. It turns out lots of things could be wrong. Is it generating search terms that aren't quite right? Or maybe we're using a web search engine that is returning results that aren't that good. So for example, is my web search engine comprehensive enough? Or is it just, maybe I picked a lower cost web search service or something that's just not returning the latest materials. It turns out for some internet articles, many web search engines will do really well. But if you ever want to fetch news, really fresh news, there's actually a lot of difference in the performance. Some web search engines are much better at having really fresh content. Some just don't update as frequently. So do I need to switch web search engines? Or am I successfully identifying the best web pages to fetch? So if I have black hole science, I think NASA.gov is very, very authoritative web page. But if a web search engine returns, Bob's Backyard Astronomy Blog.com, right? That's less authoritative than NASA.gov. Am I correctly fetching the most authoritative scientific articles versus whatever is hyped up, or maybe am I fetching a lot of random TikTok videos, rather than really scientific authoritative things? And then lastly, given all this information, am I writing a thoughtful article, right, with an LM from a final research output? So it turns out that with a pipeline like this, there are lots of steps that could go wrong, and your ability to decide what is the components you should focus your effort on that's a massive driver of your productivity and improving a system like this. And the good news is that there's actually one other thing I've seen. Sometimes I've seen a few experienced machine learning people. So actually, one thing I've seen, sometimes a team will build a system like this. And if it's a less experienced team, they build a system, it's not quite working, trying to decide what to do next. One thing I've seen many times is if you get a few senior machine learning people around, like at Stanford, I've seen this quite a few times. Sometimes a student's done a project, maybe build a system like this. If you get a few, experienced professors to look at the system, you find that our opinions on what to do next, there's remarkably little variance, right? So you find that many, experienced AI people look at it and will go, well, based on what it seems, we think this is a problem or this is wrong, we should try this. It's not that we always agree with each other 100%, but the variance is much less than you might think. And to me, that, I think there's a methodology behind how to approach these problems, whereas the variance in what to try next among less experienced engineers is much larger, right? So to me, I think there's actually, if you have a systematic way of doing error analysis to figure out where it's actually underperforming, experienced people all kind of, doesn't mean experienced people are always right, but it's just low variance, right? But then there really is a methodology to figure out what to do next. And one of the key ideas is error analysis. And I talk about this on online videos as well, but this is so important. Let's just go through. Right? And one thing to do is to look at the output of each of these intermediate steps. And it's one of these things, I know I'll say it, you probably even agree it's a good idea, but the percentage of people that will actually do it when the time comes, I found to be far lower than 100%, right? But there's just, take a handful of queries, be it, is it latest in black hole science, or should I rent or buy an apartment, or, what's the, help me make fun plans for a weekend in Santa Cruz, whatever. Some handful of queries for a deep researcher. And then look at what search terms it generates and see if it makes sense. Look at the web pages it fetches, see if they look good. Look at the top pages it fetch and see if the top web pages selected is similar or if it's materially different than what you would pick. Like my example of what if this decides to fetch Bob's Backyard astronomypage.com rather than nasa.gov, right? Then you go, oh, okay, maybe I need to change how to do that. And then also look at the final writing to see, given the source articles, is it writing the appropriate articles? And what I find is for a process like this, it turns out error analysis is often a very manual process because when the system isn't performing, error analysis or gap analysis is often a manual process of figuring out what a human would do that is better than what an AI system would do. And we're trying to inject knowledge from the human into the AI system. So because the AI doesn't have this knowledge yet, usually you do need a human time to do this. And I know, and people are talking about automating some of this and maybe there'll be progress there. But so far I find error analysis, it just takes human to look at it and have the insights into where AI system is doing something different than an expert human would be. And it's that insight that then points you in the direction for how to improve it. Right? And so often I would build a spreadsheet like this where I have a query that is, black hole science. And then another one, do I rent versus buy, in whatever, San Francisco, or, weekend activities in Santa Cruz, right? Whatever. Just have, I don't know, maybe up to 100. I find that I often have patients look at up to 100 examples, beyond 100, sometimes more than 100, but it's somewhere between 10 and 100. Have a list of queries and have a list of steps. And so the steps would be, right, search terms, what's that, web search, fetch pages, So this is what it feels like to do error analysis. It is a labor-intensive process because it's a process of identifying where a human outperforms AI to try to close the gap, right? We just do this over and over. But so what I would do is I'll sit down, often with a spreadsheet in front of me open like this, and I will run black hole science through the whole system, and then just read, are the search terms satisfactory? And if I'm not an expert in black hole science, I may need to get an expert or do a bit of work to figure that out. But if I find that the search terms to send to a web search engine are completely satisfactory, then I'll just say, okay, this looks good. Then given those search terms, I'll look at the web search results and say, did the web search engine retrieve reasonable things? And it looks good, then great. And then I'll look at, did my system, maybe an LLM, did it make a good choice in the top web pages to actually go and fetch? And maybe I found this it chose to retrieve Bob's Backyard Astronomy blog, but skip NASA.gov. Then I'll say, okay, there's a problem there, right? And then often I make a note, Bob instead of NASA, right? Just to kind of just take notes on what you're seeing. And then I'll say, given these sources, is this writing okay? Maybe it's okay. And then the process is to take a handful, somewhere between 10, 20, and 100 of articles where the performance is subpar. And it's called error analysis because I want to focus on where it's underperforming, right? So there's some articles where it's doing a great job on, I would tend to pay less attention to those, but I'll focus on finding anywhere from 10, 20 to 100 queries where it's clearly underperforming what I think a human should be doing or what I hope this will do. And then going through to just try to get a sense of how often the hotspots are in different parts of the pipeline. And so maybe for rent versus buy, I might say, boy, there's a really authoritative blogger that talks about this, but somehow web search misses. I don't know, maybe I'm using the wrong web search engine. Weekend in Santa Cruz, it's I don't know, buy into the, some hyped up tourist things rather than actually finding locally interesting web pages and so on. And then by doing this for 20, 30, 50 queries, you can then start to get a sense of where the hotspots are, right? So again, all of these are subpar results. I'm focusing on queries where the performance is not good enough. And then if I find that, 40% of the time is failing to fetch the top web pages, only 5% of the time, right, it's failing to do that. Actually, sorry, let me change. May find that 70% of the time, I'm really not happy with this. 5% of the time, web search is not good enough. Maybe 20% of the time, search terms are wrong, and maybe 20% of the time, the writing is not good enough. These don't have to add up to 100%. Sometimes you have problems in more than one column. But if this is what it turns out to be, then we'll go, well, clearly, a lot of my dissatisfaction with the results is because it's just not choosing good pages from the web search to return. So let me go focus on that. And the thing about a lot of machine learning systems is you just don't know if you don't do this error analysis ahead of time in terms of what component to focus on. And so I find that teams that know how to drive this process systematically, and it sometimes takes us hours. I read that daily schedule thing. Sometimes it takes us a few hours to go through this process to reach conclusions. But then the benefit of spending 3-4 hours on this is that it can save you weeks of otherwise heading in the wrong direction. So teams can drive this evals and error analysis process in a very methodical way. You're much better at picking what direction to work in, and that allows your team to go way faster. And there's way more than a 2x difference. So I've actually literally visited teams that have been working on something for 6 months. I go, gee, I could have told you 6 months ago this wasn't going to cut it, right? And imagine if this was the problem. We're not writing the right web pages, but for some reason, the team kept on trying out different web search engines. Maybe there's someone trying to sell a new web search service to you. So, spend a lot of time with the sales team, do a lot of integration with the website. There's actually more web search services than most people know, right? So, and I actually swap between them whenever I feel like it. So imagine you spend all your time trying to come up with a better web search service, for 6 months. And it's entirely possible. Then you could it just won't move the needle for the overall performance, which is why this type of error analysis process is so important, right? I walked through this with the example of one pipeline. The online videos go through other examples as well, but both for building deep learning pipelines and for kind of AI agentic pipelines, I think this is a very important concept to master.